Now let's see how we can generate the determinant of a 2x2 and a 3x3 matrix within our assembly language. Now, the determinant is the factor by which any linear transformation changes the area in a 2x2 or the volume in a 3x3 matrix. So we see it written as DET, which is short for determinant of the matrix ABCD. We also see it written by the two lines, and we read this as the determinant of matrix ABCD. Now, to work this out, we multiply the A and the D, and we subtract off B times C. So this is going to be relatively straightforward for us to generate in our assembly language. So I've put an example here, the determinant of the matrix 3 minus 2, 1, 4. So we're going to have 3 times 4 minus 2 times 1. So it's going to be 12 plus 2, which is a value of 14. So let's see how we're going to generate the 3x3 version. Now, it's a little bit more involved. We're going to have the determinant of the matrix A, B, C, D, E, F, G, H, I. So what we do is we take the A and then we multiply it by the determinant of E, F, H, and I. We take the value of minus B and we multiply it by the determinant D, F, G, and I. And then we take the value C and multiply it by the determinant D, E, G, and H. And I've got these written here. I've also put an example here. So in order to work out the determinant of this matrix, it's going to be 7 times the determinant of the 3 minus 1, 4, 2, minus 2 times the determinant of 0, minus 1, 3, 2, times 1 plus 1 times the determinant of the 0, 3, minus 3, 4. So if you were to work out these individual determinants and multiply them out, we're going to end up with minus 14 plus 6 plus 9, which is a value of 1. So this is a little bit more challenging in order to generate it within our assembly language. So let's go and see how we do that now. Let's work through the assembly language code for the 2x2 determinant. On the right hand side we have the calling function, on the left hand side we have the subroutine. We're going to use the same values that we used for the examples we've seen just a moment ago. So we're going to define the matrix as the values 3, minus 2, 1, 4. We're going to have the result, which will be stored in the address called DET, and that's just one memory location. We're going to push the matrix and then push the DET. So remember, when we push the matrix, we just push the address of the first value. So it's the address of the value 3. Now we've set aside the starting location for the subroutine here for the det2, which is 0 cross 1500. So we jump into the subroutine. It jumps over to the subroutine, goes through, works out the determinant, and then returns the result back into DET1, and then the program ends. So let's see the actual code. So we have to do our housekeeping. We store the result, store the values in the registers so that we can retrieve them later. We pop the return address. We then pop the position where we want the answer to be held into register R5. So that's the DET, and then we pop the value into R4. So this is the value for the matrix. So this is the first memory location, so the memory location where the value 3 is stored. And then what we want to do is we will increment the value in register R4 so that it then points to the next memory location, which is the memory location where minus 2 is stored. And then we go through and increment it again and again. So we pull out the memory locations where 3, minus 2, 1 and 4 are stored, and we store those values in the memory location defined by A, B, C and D. So we've got the memory locations for these values. stored in A, B, C and D. So what we can do is we can now retrieve the actual values out. So we can take the value in, we load the address from A into R0, so that's the address of the first value here, 3, and then we actually load the value in, so this will take the actual value 3 here into register R0. Now we do the same here for register R1, so register R1 will then contain the next value, which in this effect is the value D. So we go in and we pull out the value D, which is 4. We then do the multiplication and we get the A times D. We do the same thing for the B and the C, and we work to get the value of B times C. We then subtract R1 from R3 and it gives us the AD minus BC. We then store the final result in register R5, which contains the return address, which contains the address for the result, DET. We then load the original values into the registers as part of our housekeeping, and that's us finished. We can return to the return address, and it returns back up here, goes to the end, and that's the end of the code. So it's very similar to code that we've seen previously with other matrix manipulations. So let's go ahead and we will actually load this in and we will see it working. I have loaded the subroutine into the ROM and the program into the RAM. So whenever we run through this, we should get the determinant of our matrix 3 minus 2, 1, 4, which will give us a value of 14. Now 14 is in decimal, so in hex that is the value of E. So let's go ahead and we'll see whether this actually generates the correct answer. So this is it setting up all of the values, and we'll soon see it running through each of the values within the registers. And we can see the values starting to appear here. And then when it's finished, it clears off all of the registers back to their original values, and that's it finished. So let's have a look and see whether we get the correct answer. So the answer should be sitting in somewhere around about 8500. So the original values are here. So that's going to be the value of our 3 minus 2, and then that's 1, and this is the value of 4. And the final value for the determinant is in this box here, and it is the value of E. So it does work. So I think what we will do now is we will finish the video at this point, and in the next video we will go ahead and I will show you the code for the 3x3 determinant. So thank you for listening. I'll get you in the next video. Goodbye.